In this video, I want to talk about what the boundary conditions are to solve the differential equation for a fin. And in the last lecture, we derived the equation for what a fin, or the general solution for the fin equation. Okay, so this is for a uniform cross-sectional area. This is our differential equation. This is the general solution. And the idea is to solve for what these constants are, we need to know what the boundary conditions are. And so there's several boundary conditions that are exclusively used for these kind of equations. Let's keep in mind we're talking about this uniform cross-sectional area, okay? And we're talking about a one-dimensional equation, okay? So our differential equation is one-dimensional, in this case, z, okay? So it's one-dimensional in z, so it's talking about the temperature down the length of the fin, okay? So the temperature is just changing down the length of the fin. We've proven this earlier. But where would these boundary conditions be? Okay, so we have convection all along the fin. But we've taken into account convection along the fin. When you do the energy balance for a fin, we took a differential control volume, and we said there is some convection loss from the surface. So if you're talking about in the x, or now it's dimensionless, so this is going to be z direction down the fin, we really need to know two spots. And that's at the base of the fin and at the tip of the fin. So we don't know what's going on there, but we have taken into account all the convection losses from the surface area of the fin. We took that into the energy balance. So that's in the differential equation. So the boundary conditions are on the z direction or x direction. So what are they? Boundary condition 1, we're going to say, is at the base of the fin. Okay, so at the base of the fin, the temperature is just T base by definition. Okay, so if you look at how we define theta, it's T minus T infinity over T base minus T infinity. So if you put a TB here, this is just 1. Okay, so that means theta at 0 equals 1. Okay, and to be clear, let's write what it is in the real temperature. T at 0 equals T subscript B, T base. Okay, so that's the basic. I mean, that's it. By definition, there is this is steady state heat transfer. So by definition, there is a temperature, a base temperature there. Okay, that's fine. We can solve that base temperature by considering what's going on away from the fin. But what's happening at the tip of the fin? That's an interesting question. And there are 4 common conditions for boundary condition 2. So this is at the tip. So this is at z equals 1. So this is at the length of the fin. This would be x equals L. So z equals 1. What are the 4? Number 1, you can have convection. Okay, this would make perfect sense as you have convection along the length of the fin. You also can have convection at the tip of the fin. And so this is Newton's law of cooling, which is minus h a delta T. But keep in mind here the areas we're talking about. So if you're looking at through the fin from the side, along the length of the fin, it's the cross-sectional area that Newton's law of cooling is occurring over. And at the tip of the fin, this is the surface area. Okay, the surface area of the fin. At the tip of the fin, it's this area where there's heat loss. So this is the cross-sectional area that occurs along the length of the fin. So these are 2 different area terms when we're considering convection losses from the tip. Okay. So what is the expression Newton's law of cooling at the tip? Okay. So what we need to do is we need to say conduction Q equals convection Q, heat transfer rate, at x equals L, which is the same as z equals 1. Okay. So we need to say there's no generation. So energy getting to the tip of the fin equals the energy leaving the tip of the fin by convection. So the expression there is minus k dt dx. Well, technically it's minus ka c, cross-sectional area, dt dx at x equals L is equal to h, cross-sectional area, t at L minus t infinity. Okay, so this is the conduction right on the left-hand side of this surface equals convection right on the right-hand side of this fin tip surface. So that's straightforward. It's a little bit better to write this dimensionless because we solved our equation dimensionless for theta. So let's write this in terms of theta and z. And so what we need is an expression for dt. We need d theta. Okay, so let's take what we had for theta let's bring the denominator up here and take the derivative, okay? So this is going to be TB minus T infinity times theta equals T minus T infinity. Take the derivative of each side, and you're going to have TB minus T infinity d theta equals dt. Let's do the same thing for x. Okay, so let's bring the L up here and take the derivative. So this is going to be L times Z equals x. Scoot this up a little bit here. And then this is going to be the derivative, L dz equals dx. So now we can plug these expressions in for the derivative term. We have minus k. These areas are going to cancel out because they're evaluated at the same spot, the cross-sectional area at the tip, which is constant anyway in this example. So k, and then that dt is going to now be tb minus t infinity d theta. And then dx is going to be L dz. And this is evaluated at, instead of x equals L, it's going to be z equals 1. Okay, so that's the left-hand side. And the right-hand side is h, and then t minus t infinity equals this. So this is going to be tb minus t infinity theta. And then these temperature differences are going to cancel out. This is the beauty of non-dimensionalization. By the way, this is theta at z equals 1. And we're going to get minus d theta dz at z equals 1 is equal to hl over k theta at 1. Okay, so I've multiplied the L over. And this is really interesting. This is our BO number, and this is a ratio of convection at this spot. So this is along what length compared to the length scale? This is along the length of the fin. So if you're talking about heat transfer along the length of the fin, it's the ratio of conduction to convection along the length. A little tricky with fins. It's not like a plain wall where you can easily look at your BO number, because we also have heat losses that are on a different length scale. So heat loss is perpendicular. So this is kind of a BO number characterized by this direction, but that's not our only loss. Okay, so you'll still have a temperature loss due to these perpendicular heat losses. But it's still going to be interesting to compare, you'll see. This is the boundary condition we would plug in. Now, what's the boundary condition for an adiabatic fin tip? What does an adiabatic fin tip means? It just means that, I'm going to draw it like this. There's no heat loss from the fin tip. Okay, so this is an assumption. Maybe the fin tip is insulated, or maybe this is just an assumption you put in because it makes the math easier. How you would write that is dt dx at x equals L is equal to 0. And you can plug these terms in here, but they're going to divide out anyway because it's 0 on this side. So this is the same thing as saying d theta dz at z equals 1 equals 0. Okay, and so instead of saying it's an adiabatic fin tip, you could also just assume that there's negligible heat loss from the tip, meaning the heat that you do lose there is insignificant compared to the heat that's lost along the surface area. So if you had a really long fin, you'd imagine that the surface area is much larger than this cross-sectional area at the tip. So maybe in that case, this heat loss at the tip doesn't matter. And another way you could look at that is think of this as your BO number. Okay, so if this is your BO number, I'm going to put a subscript L, meaning it's characterized by the length of the fin, not the thickness of the fin. So we're going along the length. Having negligible heat loss at the tip is the same thing as saying your BO number is much less than 1. Okay, so meaning that your convection is very good, but your conduction is poor. I'm sorry, your convection is very poor. Where is it? H. H would be very low for your BO number to be less than 1. So it means that, heat can conduct down here, but the convection of heat from the tip surface is very low. You have negligible heat loss from the surface, so your BO number would be very low. In that case, this would go to 0, and you're left with, by definition, the same boundary condition. Okay, so this is also valid, and you could just plug in what H needs to be relative to K for this boundary condition to be applicable. Maybe 2 orders of magnitude is a good estimate. 2 orders, so this could be 0.01 or something. But yeah, adiabatic tip is one option. So there's 2 more boundary conditions. The next one is a fixed temperature at the tip. And this is kind of an interesting one because, you'd have some solid surface with an extended surface sticking off of it. But instead of it just being stuck out into the air, it actually attaches to another solid surface. Okay, so it's more like these 2 solid surfaces have basically a fin attached to each other. Their fins come together. So this would happen, for example, what if you have 2 skyscrapers and you had a boardwalk in between them? This is an example because all that you need for an extended surface or for a fin is for the heat loss due to convection to be perpendicular to the heat diffusion due to conduction. Okay, so in this case, even if you're connected, if this fin is touching another body, you still have convection being perpendicular to heat conduction. So it's still a fin. So there's a lot of different things. You can think of a strut. These T struts that would go in a construction site. Those are fins. Like if you took this kind of T strut framework, like a beams for construction, they look just like this in a cross section. And so you get a really interesting heat transfer problems going down this. As you keep in mind, they're going to cool from that connecting strut surface. So what is the temperature here? This one's a little straightforward because all we're saying is that T at L equals T2, whatever it is. So another way to say it is that theta at 1 says that Z equals 1 is X equals L is some arbitrary theta 2. In this case, theta 2, taking the definition of theta, is T2 minus T infinity over TB minus T infinity, okay? So this is just saying there's a fixed theta or fixed temperature, or however you want to write it, at the end, okay? And in this example, this is the base. We're saying this is the end. But you could write it the other way around too. Now, finally, our 4th boundary condition is an infinite fin. This sounds crazy, but if you had a fin that's infinitely long, and it's not that crazy because it turns out that the math can be a little bit easier if you assume it's infinite. And you just need to prove to yourself, when can I assume the fin is infinite? But if you do assume it's infinite and you have those conditions, this is what the boundary condition would be. T as X goes to infinity equals T infinity. Of course, look, if we go back and plug T infinity into our theta expression, that would mean theta equals 0. So that means that theta as Z goes to infinity is 0. That's the same thing, dimensionless. So those are the 4 boundary conditions. Here's kind of the summary. We've got a fin of uniform cross-sectional area. We have an equation to solve the constants in the differential equation that we solve, the general solution. We need to know the boundary conditions on X, or in this case, dimensionless Z, which would be this direction. So we've got the temperature at the base of the fin, which is written here. And we also have a temperature or some sort of boundary heat flux condition at the tip of the fin. And we've talked about 4 different ones: convection, adiabatic tip, fixed temp, infinite fin. And there's all very interesting relations between the solutions of these different boundary conditions. And these are the ones you want to plug in to solve for the constants.